All right, so we're going to start on page 50, but before we begin the new material, we want to take a look at some old material, just make sure we're comfortable. This is one of the problems from the homework. It's complicated because it has fractions in it. So remember the big tool that we developed last class was the quadratic formula, but first we need to get one side of this equation equal to 0. So how about we move the 50 over? So subtract 50 from both sides. We get this. Melanie, do you know what number this was in the homework?
11.
Thank you. Okay, so if you didn't get this one, you're welcome to update your homework now with whatever we write up here. Okay, so we're going to do the quadratic formula, but it's quite tricky to do it with fractions in it. It's totally fine to do it, and you can get the right answer, but it's a lot more work than it needs to be. First of all, can anybody look at this and tell me what a is equal to? Remember, ax squared plus bx plus c is our standard, although in this case it's as squared plus bs plus c. What is a? It's 1 over 24, which doesn't even appear in the equation. So you really need to do work. If you've got fractions like this, you need to recognize that s squared over 24 is the same as 1/24 times s squared. And then plus 1/2 s. Right, you got to peel the s's off so that you can really identify the numbers, the a, b, and c. And then minus 50. So already I'm not thrilled leaving it with the fractions because it means you got to do work to figure out what the a and the b and the c are. How much is b? Remember, it's the number touching the x. It's 1/2. B there. It's 1/2. And then c is the last guy, negative 50. So it is very possible to do the quadratic formula with the a, b, and c that we've written and get the right answer. But it's also quite a bit of work because you'll have a lot of calculating to do with fractions in it. You're going to end up with a fraction inside of that big square root. You know, in the quadratic formula has a big square root. Fractions inside of square roots means there's more work to do. So not only is it hard to get the right answer, there's more work involved than if we do the alternative. And the alternative is to get rid of all the fractions as the first step. So how about we say, or we get rid of the fractions. The way we do that is to multiply both sides. We have an equation, so we got to do the same thing to both sides by the lowest common denominator. Okay, looking at these denominators, I have a 24. I have a 2. What is the lowest common denominator when we have a 24 and a 2? It's 24. You're looking for you got to find something bigger than these numbers. So we need something that both 24 goes into and 2 goes into. The 50 we don't have to worry about because it's not a fraction. So the LCD in this case is 24. So I'm going to copy that top black equation. 0 equals s squared over 24. I'm going to leave a little space in front of each of these guys. Minus s over 2 minus 50. Yes. It's the smallest denominator that will work. Lowest is what we're after. There is something called the greatest common divisor, which would be the biggest number that goes into all the numbers. What's the biggest number that goes into 2 and 24? Is 2. 2 is the GCD, the greatest common divisor. 24 is the lowest common denominator, also called the least common multiple. So there is a corresponding greatest thing, but we want the lowest thing. Oh, thank you. It is a plus. Good catch. Okay, so we are multiplying everything by 24. So let's multiply the 0 by the 24. Not a big deal. And then we're going to multiply the whole right-hand side by 24. I'm going to write something that I don't want you to copy, and then I'm going to write what I actually mean. It's this entire thing times 24, right? Both sides getting multiplied by 24. But I'm going to jump to the next step right now, where we take that 24 and we distribute it into the parentheses. So really, how many 24s am I going to actually have here is 3. So that's why I left the space there, was so that I could put in front of each of these guys a 24. Okay, and then 24 times 0 is still 0. What happens in the next one? We just get s squared because those 24s just straight cancel. Plus 24 divided by 2 leaves 12. 12 what? 12s. Minus, and then 24 times 50, we need to do that. And the solutions using the quadratic formula on this thing will be a whole lot easier to find than if we had done it with the original fractions. So then I'm going to say over here, dot, 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 use the quadratic formula, QF, quadratic formula. So you give me an equation with fractions in it, my first step is to multiply it by the lowest common denominator. That gets rid of the fractions. And then I'll do whatever I need to do normally. Questions on that one? What's that, Ben?
So you don't necessarily have to convert to fractions.
To decimals?
Not to just go like to. Because I did I changed the s over 2 to 12s over 24.
Oh.
I have absolutely no idea how.
Yeah, you found the lowest common denominator, but then you actually kept the denominators there, and you made one fraction, which I guess was probably this thing we have at the bottom divided by 24. Yeah, which is fine. And then if you multiply by 24, you'll get exactly this. So I think that, yeah, I think the easiest but not only way is to multiply by that 24 first. Okay, so I promised you last time there would be a nice, memorable way to get that quadratic formula into your head, right? It's this very complicated, long thing. So let's go back. So you have it on what page? It's the page before? So just go to the page before. Yeah. So on the page before, in the middle of problem number 11, or number 10, I mean, you'll find the quadratic formula in all her glory, right? X equals negative b plus minus, all that stuff. So how are you supposed to remember this crazy complicated formula? Well, again, on the quest, which is coming up, I will provide this formula for you. This is right at the top of the quest. So you don't need to memorize it at this particular instant, but you know, the more familiar you are with it, the easier it'll be to apply it. So it turns out there is a way to remember that formula by thinking about a very famous nursery rhyme called Pop Goes the Weasel. You guys know this one? Okay.
No, we're like crappy stuff.
Okay, so that is the quadratic formula sung to the tune of Pop Goes the Weasel. Just a way to remember it. Okay, so we begin now on page 50, the new stuff on page 50. A couple of quick announcements. First of all, this week is spring week, so a couple of people actually were downstairs for part of the festivities earlier today. At lunchtime today, there was a great jazz ensemble down in the dining commons. There were some snacks and some drinks and good music, and t-shirts for $2. Okay, there is something happening every day of this week. We won't see each other tomorrow, but tomorrow, if you are on campus, around the lunch hour, there's going to be a hot dog truck right in front of the main building. So free hot dogs and soda. So check it out. I don't know exactly what times. I think it's something like 11 to 1 or so. T-shirts you can buy all week for $2. Yeah. Okay. Next thing is Wednesday, right before our class, which is why I'm sharing now. Wednesday is game day between 10 and 2 in the dining commons on Wednesday. You can go to the cafeteria, free entertainment and food. large-scale games like chess, Connect 4, and Jenga. There's ping pong, there's air hockey. I am very good at foosball, so if you find me there, I will play and I will kick your butt. I suspect it's from the Math Club's purchase of the Connect 4 boards. So yeah, so go check it out right before class. I'm going to try to get down there and hopefully we'll see some of you too. Any questions on that? There's other stuff happening Thursday and Friday. Maybe we'll chat about that on Wednesday. All right, our calendar. Today is day number 2 of the quadratic formula, and we're also going to talk about something called complex numbers. Raise your hand if you've seen I in a math class before. Got a couple of them. That is our main topic for today. I. Okay, so all right, so today's the 22nd. Wednesday, we're going to talk about quadratic models. Friday, we have our quest. However, because there's no review day, I wanted to make sure 2 things happen. Number 1, I'm happy to spend a little bit of time on Wednesday reviewing, but only if you guys come in with questions. If you just come in and don't have questions, then we're just diving into the new stuff. But if you have specific questions heading into Friday's quest, bring them. We'll start there on Wednesday. Also, the material for Wednesday is not on the quest. So at the end of today, that will be the end of the new material for the quest. Sure. So the quest is on classes 24 to 30, which is from here down to here. Okay, that is what the quest is on. Yeah, the previous quest only went up to 23. So we've got essentially the topics are this: factoring, more factoring, solving quadratic equations by factoring. You get the hint, factoring is a big idea here. And then a little bit of graphing parabolas, and then quadratic formula with this I stuff that we're about to do. Evan.
I haven't gotten a chance to look at the packet yet. Does it have like a really practice?
It does. So the practice problems appear right after today's material.
Okay.
So we can just zip right there real quick. Right here. Not right there. Right here, 56. Yeah, page 56, you will find the standard practice problems. You will also find videos on YouTube if you search. Yeah, good. You're welcome. Michelle.
Bring in the 6 steps.
6 steps for the parabolas. Let me. Okay, so it's a good question. Can we bring in a sheet with the 6 steps for the parabolas? So here is what I will do for you. So I don't teach this class in a vacuum. I'm teaching it along with some colleagues. So I'm going to ask my colleague what she thinks about the parabola process, and I will get back to you on Wednesday, okay? Okay. And, parabola process. Okay, good question. Anything else before we start the new stuff? In your minds. In your minds. Okay, so let's go ahead and go back to page 50. Here we go. Okay, page 50. We're going to jump to number 2, and we will start with Sebastian. We will start with Joe. Okay, take a look at the graph in part D. So the picture in part D has how many x-intercepts? 0, right? But the quadratic formula, we know we can use the quadratic formula and it will find us the x-intercepts. So what will the quadratic formula do when the answer is there aren't any? That's one question from today, okay? And then part B, we are over to Dan in the back. Okay, so if you don't care about what the actual solutions are, but really just what kind of numbers they are, am I going to get 2 messy numbers? Am I going to get 1 nice number? What kinds of answers are we going to get when we solve quadratic equations? We want to know if there's a shortcut. Those are the 2 things we're after today. So let's look at number 3. Sebastian. Okay, so let's give it a shot. I'm telling you the equation of this parabola is y equals x squared minus 4x plus 5. We're going to use the quadratic formula. So remember quadratic formula, can you guys fill in the not numbers, but A's, B's, and C's? Can you, I'm just kind of asking if you, how well do you know the quadratic formula at this point? So try to not look at the answer and just see what you can fill in with A's, B's, and C's. No numbers, just A's, B's, and C's for right now. You understand the question? I just want to know if you know the formula. So what's the first thing in the formula? Yeah, that's what I'm asking, is if you have it memorized right now. That's all. Okay, so what comes first? Negative b plus or minus square root b squared minus 4ac, all divided by 2a. Okay, so now that we have the formula, go ahead and plug in the numbers, and let's see what we get. So we're plugging in the a's, b's, and c's from the equation into the, so here's the equation right here. So where we have negative b, what are we putting? Positive 4, right? Because we're doing the opposite of negative 4. B squared, how much is negative 4 squared? Yeah, what do we get when we square it? 16 minus 4 times A times C. Minus 20 is good. All divided by 2A, which is 2 times 1, which is 2. Yeah, that's the issue. 4 plus or minus square root of negative 4 divide 2. Okay, so ignoring the very strange looking thing on the board, are there any questions in getting to this point? Are we okay with the quadratic formula, just plugging in? Evan?
I just, I was trying to figure out how you got 16 minus, got the 16.
I think Michelle got the 20. Michelle, where'd that 20 come from?
Right, okay, yes.
Yes? Okay. All right, Michelle just has to point to people and they answer for her. That's great. What power, just there. Okay, so what is very troubling about this answer? Isn't there something quite unusual about that answer? Square root of negative 4, right? And for the longest time, if you ever got the square root of a negative, you would just say, oh, this is not a real number, and that would be the end of the game. So now we're going to continue the game by introducing, we're changing the game by introducing something that will allow us to handle the square root of negative 4. But it's really quite troubling a little bit because how much is the square root of 4? 2. And how much is the square root of 64? 8. So can we find a number that when you multiply it by itself, you get negative 4? Yeah, if you multiply two positives, what do you get? Positive. But if you multiply two negatives, what do you get? Also positive. So it doesn't feel like there's any way to take a number and multiply it by itself and get negative 4. And that's what we're trying to do here. Okay, so let's hold off disbelief and we'll move on to number 4. Katrina. Evan.
Yes, mathematicians have created a number system called the complex number system. These complex numbers allow us to complex numbers. And in medicine,
Thank you. Drew.
story is abstract. Question how to define 16th century Italian mathematicians tried to solve efforts led to the invention of a new classification definition. What positive square root negative 1 that is pi.
Okay, put some stars around that. That right there is the most important definition for today. The square root of negative 1 we are about to give meaning to. What does it mean? Oh, still kind of hard to describe, but we're just going to assign a letter, and we're going to say anytime we see square root of -1, we're going to call it I. It is not so unusual to denote a very important number with a letter. What is the maybe most famous number in math that has a letter? So x would be a variable. It is a letter. But pi, right? Pi is a letter, yes? It's a Greek letter. But you guys know that pi is the symbol we've given to this really important number in math that has to do with circles. Anybody know the first few digits of pi? 0.14, 159. Do you know any more?
0.1415926.
Good job reading.
No.
So in math, we have done this before where we take a number and we just call it a letter. Instead of 3.14 and then change, we're going to call it pi. Instead of the square root of -1, we're going to call it I. It is a perfectly good number. We're just giving a letter so that we can refer to it. Let's move on to 6. We're up here to Dan in the front. Okay, so let's take a look at the square root of -4, which is the problem that we're facing here. First of all, is it okay to write that -4 as -1 times 4? Same thing. And now we're going to use this property about radicals that says, hey, if you have a product inside, you can make it 2 radicals with a product at the end, right? We've done that before. But now we see this new symbol, square root of -1, and we gave that thing a name. What is the square root of -1 called? It is I. And so the square root of -1 simply becomes I. And the square root of 4 happens to be a nice number. That's 2. So we'll write the 2 first, and we get 2i. Square root of -4 is 2i. Let's try the same thing on the next part. Square root of -49. First, we're going to pull off a -1 just so we have multiplication. So that's -1 times 49. And then just try to mimic the idea from right up above. I'm going to write that as 2 radicals multiplied. Then one of those radicals is about to become a letter. Seven I. Okay. What's the problem going to be with the square root of -12?
There isn't a perfect square.
Yeah, right. 49 was perfect and 4 was perfect, but 12 isn't going to be. But we still follow the same process. Yeah, so we're going to write this. I'm just going to do it as a -1 times 12 just to really kind of copy the same thing we did up above. And I get I times the square root of 12. And that's the part where it's different because the square root of 12 is not a perfect square, so we can't do anything there. We will. So before we go further, everybody okay with that I square root of 12? And then maybe we'll start to kind of get a shortcut so we don't have to write this out every time. If you see a negative in a square root, you just stick an I in the front and make it positive, right? Do we see that's the pattern, right? Like that square root of -12 became an I, square root of +12. That's what happens every time. So if you see a negative, just stick an I in the front and then make it positive. It's still in the square root, and if it's a nice number like 49, then you can deal with it. But even if it's a not so nice number like 12, you just copy it. I will also say that it is not typical to rewrite this in this order. It's correct. It's fine to write the square root of 12 times I, just like we wrote 7 times I. But the reason we don't do that is if you accidentally make your square root symbol just a little bit too long, all of a sudden it looks like the I is underneath, and it's not. So that's why typically if there's a radical still there, you leave the radical at the end, I in the front. Okay, but Katrina's right. We can go further with that 12. So you're going to break the 12 down into 2 numbers, one of which is nice. 6 and 2, is that useful? No. What's useful? 4 and 3. And so this is I times 2, square root of 3. And it is common to put the 2 in the front, 2I, and then write the radical at the end. Okay, and remember how we were getting a shortcut here that basically said if you see negative 12 in there, you put an I in the front and then make it positive 12 still in there. So that's the same basic idea as what's written here with the K's. If you see a negative, you just put an I in the front, make it positive. Right? So that's our basic definition. Okay, we'll go to Teresa for 8. Okay, so let me just give you a couple of examples of these complex numbers. You could have the number 3 plus 7i. That is called a complex number because it's of the form a plus bi, something plus something times I. Another complex number, negative 2 minus I square root of 3. Some number plus I times some number with a liberal use of the word plus because negative numbers, positive numbers, it's all basically the same. So that's another complex number. How about 2i? Is that of the form something plus something times I? Yeah, what's the first something? How much is a if I don't have it written? It's 0. So 0 plus 2i is a perfectly good complex number. What about, so I'll put here in green, 0 plus 2i, it looks like a plus bi. What if I just had the number 17? Is that a complex number? A or B, which one of them is 0 in this case? Is the B. So I could write in here in green, 17 is really the same as 17 plus 0i. Right? So a number plus another number times I, that's what complex numbers are. It doesn't look like it doesn't have a plus. So let's look at that negative 2 minus I square root of 3. A is the first number. What is the first number? Is negative 2. So that's how we handle the negative there. B, no, the I is part of the formula. The B is everything else except the I. So what's everything else in here? Everything except the I is supposed to match up with that. So how much is everything else except the I? Is the square root of 3, and what else is the negative? That negative square root of 3 is the thing touching the I. This isn't really a detail I want to worry about right now, or at any point. But would you agree that negative 2 minus I radical 3 is the same as negative 2 plus negative radical 3 times I? All right. Right. Subtraction. Maybe at some point in your past, you every time automatically wrote subtraction as adding a negative. So that's all we're doing. We're just saying that that right there is the B. It happens to be negative, which is why I said addition subtraction doesn't much matter. Okay. Don't worry about that detail if you didn't quite get it at that point. What we should worry about is number 9. So we're going to finish solving the equation that we started with today. We were here before, 4 plus or minus square root of negative 4 divided by 2. So now that we've seen this I business, we can deal with this. 4 plus or minus. Let's just use the shortcut. If you see the square root of negative 4, what do you put in the front? I, and you make it square root of positive 4. That's it. If you see a square root of negative, put an I in the front, make it square root of the positive. And then in the next step, we'll do the square root. 4 plus or minus I, and then what is the square root of 4? 2. Yeah. So we're going to split this up into 2 fractions. There is going to be a lot of canceling that happens. Like it looks like the 2 on the bottom might cancel with the 4, or it might cancel with the 2 on the top. It cancels with both, but I would always encourage folks to split this up into 2 fractions. 4 over 2 plus or minus I times 2 over 2. See that? And just about every time I do the quadratic formula, I do this. I split it up into 2 fractions and then see if I can simplify. 4 over 2 becomes 2 plus or minus I times 2 over 2, I. That's our answer. Stop. Nope, that's the last game. So that's it, 2 plus or minus I. So let's real quick look back at graph D. Again, how many x-intercepts does it have? It has none. So how did that show up when we did the quadratic formula, which will find us the x-intercepts? It showed up with an I in it. And we don't see anything that has an I in it. We only see the regular real numbers up here. If it has I's in it, it exists in this graph that's actually quite difficult to even imagine, but we won't see it in the graph that we're doing here. So you get something with I's, it's because the graph never hit the x-axis. This semester we will not graph the I things, but if you take 107, you will graph the I things. Yeah. Something to look forward to. All right, let's move on to number 10. Where's our next reader? It's up here, Tenzin. Shh. Okay, thank you. So let's, maybe I should have put some space here at the bottom for this, but let's just list a few of the very famous, well-known sets of numbers to make sure we're clear on the vocabulary. So if you have a number, so here are the two words that I'm really asking if you guys know. Rational number versus an irrational number. And it's a little unfortunate that we use these words because rational in outside of a math context means, you know, like kind of clearly thinking, level-headed, right? A rational person. And somebody who's irrational is kind of unpredictable. We don't use the words rational and irrational because we're making that kind of judgment. We use those words because we are talking about ratios and things that are not ratios, right? Ir means not. So, okay, so a rational number is just a ratio. 1/2, -2/17. Those are rational numbers. I'll also put 1/3 up here. And rational numbers, if you write them as a decimal, have two options. What is 1/2 as a decimal? It's 0.5. How about 1/3 as a decimal? It's 0.333 forever. Somebody with a calculator, 2/17. I don't expect we just know that one, but we can find on the calculator what it says. All right, we actually need some more. 11764. What is it? 706. I feel like I probably picked 17 as a little too, all right, 17 is a little too big because of the limitations of the calculator. Let's change that to 7. 2 7s. As a decimal, what is this guy? Do we see a pattern yet? Anybody know what the next digit is without a calculator? It's 7. It is repeating. It is repeating the 285714. ... So that block right there repeats forever. So when you have a rational number, it either means you could write it as a fraction, like any of these guys, or if you choose to write it as a decimal, there are two possibilities. It either flat stops, like 0.5, and it just ended, or if it goes forever, no problem, it's going to repeat. And it could repeat in a very simple pattern, like all these 3s, or it could repeat with a block of 6. When I did 2 17ths, the block could actually be 16 things long, which is why I had to change it, because the calculator, it's only because the calculator doesn't have enough things to show me. But if I had a very strong, you know, like type it on the computer, if you had enough digits, you would see that 2 17ths repeats every 16 spots. It's no problem. The irrational numbers are the ones that you can't write as a fraction, or the ones that you, if you write them as a decimal, they go forever, but they never repeat. Pi is a very famous irrational number because it's equal to 3.14, and then I think, Drew, 26 is good. And it goes forever, and it never stops, and it never repeats. And that's very different from the decimals that we had over here in black. And it turns out there's no way to take pi and write it as a fraction like we did here. There are some approximations, like if you guys heard 22 sevenths, Maybe in some math class you've had before, you use 22 over 7 as an approximation for pi. You can type in 22 over 7. You'll get something that's pretty darn close to 3.14, but it does repeat, which means it's not pi, because pi never repeats. There are many, many other numbers that are irrational, and it's very easy. Yeah, we're not, no, infinity's a concept more than a number, say. But the square root of any number that doesn't have a perfect, that isn't a perfect square, those are all irrational. So the square root of 2, square root of 3, how come I can't write the square root of 4? Because that's just 2, right? And 2 belongs in the left-hand list, but the square root of 5 and the square root of 6 and 7 and 8 are all over here in the irrational side, okay? So here are our two big classes of numbers. Oftentimes we focus way more on the numbers that are black than the numbers that are green, but that doesn't mean the green numbers are any less important. Okay, so let's come back up here and take a look at this picture for our graph A. We're going to write down the nature of the solutions for the quadratic equation, which really means finding the x-intercepts. And this word nature I haven't defined, but we'll do an example and you'll see what I mean. So the x-intercepts, how many x-intercepts do you see in graph A? You see 2. And if you just had to guess, what's the left one? -6, and the right one is 1. -6 is in which list? Is it a rational number or an irrational number? -6 is rational. It belongs over here in this list. You can just write it as a fraction, -6 over 1, if you want to. Right? It certainly doesn't go on forever as a decimal. It's just -6, and it stops. So in this case, the nature of the solutions are, there are 2 of them, 2 x-intercepts, and they are rational. 2 rational numbers. Without really worrying about what they are, we're just saying how many there are and what kinds of numbers there are. There are 2 of them. They appear to be both rational numbers. For graph B, how many x-intercepts does it look like it has? It has just the 1, so we can right away start just writing 1. And what number does it appear to be? 2, which is what kind of a number? It is rational. So 1 rational number is right here. So again, I haven't defined the word nature, but what I mean is tell me how many solutions and tell me what kinds of numbers they are. Let's look at the next page. How many x-intercepts in graph C? 2. You guys remember we estimated these before? You know, like -3.4 something and 1.49. Do you guys remember how ugly those numbers were when we typed them on the calculator? And we had to use the quadratic formula for this one, which meant we had a square root in there, which is why we got all those messy numbers. So if you are getting messy numbers, is that in the rational side of things or the irrational? It was irrational. It was decimals that never repeated. It was radicals. These represent 2 irrational numbers. And I don't mean to imply that we're supposed to just be able to look at the graph and decide whether the numbers are rational or irrational, because what we actually saw in class was that this was 1.49 and change, whereas what if it were actually 1.49 exactly? What kind of a number is 1.49? That's a rational number if it stops. But the change meant that it went forever and it didn't repeat. And there's no way for me or you to look at that graph and decide whether, oh, it's exactly 1.49 or it's 1.49 and change that goes forever. So you're not supposed to just be able to look at a graph and know, but we have prior knowledge about this one. We remember that it was 1.49 and then lots of stuff. Okay, and then the last one over here, how many x-intercepts? There were no x-intercepts. And what did that mean we got when we used the quadratic formula? We had i's in it. And then how many answers were there? Let's go back to the one we had with the I. Where'd it go? Right here in the box. 2 plus or minus I. That really means 2 different things. It means 2 plus I, and it also means 2 minus I. So how many answers is that? 2. And what kind of numbers are there? They're not rational. They're not irrational. They are, we didn't use the word imaginary today, but I appreciate some of you guys know that word. They are complex numbers. That's the word we use today for anything with I in it. So we can come down here. We can say there are two complex numbers. Okay. What's that? What? Yeah, it means that the solutions that we got right here. So I know there's no x-intercepts, but the equation that this graph came from was, what was it? X squared minus, I don't remember, 4x plus 5. That's the equation that was graphed, was a y equals that thing. And when we want to find the x-intercepts, we make it equal to 0 because we know that on the x-axis, the y is 0. And when I solved this equation, the answers were 2 plus or minus I. So I'm just looking for, forgetting about the graph for a second, just thinking about an equation. And I solved that equation and I got 2 plus or minus I, which is what I'm describing here. So more important to me, so we're making a little bit of connection here between what the graph looks like and what kinds of solutions an equation has. But it's an algebra class. And there's an algebraic way to look at an equation and decide what kind of solutions it has that doesn't rely on the pictures at all. So that's what's coming up here in 11. And this is quite important for us coming up on the quiz. So let's get through this and make sure we're good with it. Where are we now? Glenn, 11?
How does this relate to the quadratic formula? There are only inputs you would get, then in the kind of answers we would get, then calculations is a shortcut. That's basically get from the quadratic formula only depend on what happens inside the radical square root squared minus 4.
Okay, so you guys have seen that. That's a part of the bigger quadratic formula. Square root of b squared minus 4ac. So we're about to give a name to that thing inside the radical, this b squared minus 4ac. Not with the radical itself, but just the thing inside. It is called the discriminant. Discriminant. And so let's go ahead and fill in the table down here, calculating this newfound thing called the discriminant. So all you're doing for each of these examples is b squared minus 4ac. We'll do the first one together, and then with your neighbors, you're going to do the other three. B squared minus 4ac. B squared, so that's supposed to be 5 squared, minus 4 times, what's A? 1 times what's C? Negative 6. I really think it's better to do these without a calculator. It's very easy to go wrong when you type in complicated things on the calculator. 5 squared is 5. And then minus minus makes plus 24, which is 49. That's the end of that one. We're going to fill in the last column after, but right now just move on to the next row. You are just doing b squared minus 4ac. If you finish the one in the second row, check with your neighbors before you move on to the third row. So we're looking for 3 other numbers here. So let's come back together and analyze now. The first discriminant was 49. But remember, the discriminant is the thing that's underneath the square root in the quadratic formula. So in your mind, I'll draw it here in blue, you're imagining the square root of 49. Is that a nice or not nice number? That is a very nice number. So when I do the rest of the quadratic formula, it's only going to have nice numbers in it. Do you buy that? So we'll write the whole thing. Negative b plus or minus square root of the discriminant that we just found divided by 2a. B is a nice number. A is a nice number. The only question is what's going on right here. That's the thing that completely dictates whether the whole thing is a nice number. So if you get square root of 49, that's a nice number. It's 7. So all told, the entire thing is nice. When we say nice, do we mean irrational or rational? Rational. So here we're going to say that the nature of the solutions, they are going to be rational. There's going to be that plus or minus there. So how many different answers are there? 2, because the plus and the minus. So we get 2 rational numbers. And that's going to happen anytime the discriminant is what kind of a number? Is a perfect square. That's what made that work. Let's skip the 0 for just a second. Let's jump down to the 24. Again, the 24 is going to be the thing in the radical. Is the square root of 24 nice or not nice? It's not nice. Even if you can simplify it, even if you can think 24 is really 4 times 6, still you'll have a 6 in there, which is still not nice. So you don't even have to worry about, can I simplify it any? You just need to know, is 24 in the bottom row of these yellow numbers here? It's not. It's not a perfect square. So what kind of numbers will I get, rational or irrational? We're going to get irrationals. There's still a plus or minus, so there's still 2 of them. So I'm skipping a row, so just make sure you put this in the right spot. And all of this is summarized down below. We're kind of building it. And then we'll look at the summary. Let's look at the last row. The discriminant there was -4. -4 is inside of the square root. What kind of numbers are going to happen when you have a negative in the square root? Is those complex numbers, right? Because you'll have i's inside of it. There is still a plus or minus. Yet again, there are 2 of them, and they are complex. Did I call them imaginaries? I will change that. Thank you. Yeah, I hear that. I hear that. Let's fill in the row that we missed. So far, what's the same about all the rows in our? They always have 2, right? Seems like it will always have 2 because there's a plus and there's a minus. But yeah, it's going to be different in this row that we skipped. Here, the discriminant is 0. So inside of this square root, I'm imagining a 0. What is the square root of 0? It is 0. So when I do this plus or minus 0, I am first adding 0 and then I am subtracting 0. And what happens both times? I get the same thing. So when you have a 0 there, this thing completely disappears. Adding 0 is the same as subtracting 0, is the same as it not being there at all. So how many solutions do you get in this case? Just the one, because the plus or minus didn't add anything. So this is the kind of outlier. It's different from everything else. There's 1. Yeah, is it rational or irrational? Even if p is negative, still going to be a nice number sitting out there. Remember, the only thing that's going to determine whether the final answer is nice or not is that square root. The square root is the part where you maybe get some decimals that go forever. So this is just -b, that's a nice number, divided by 2a, that's another nice number. This one gives me 1 rational number. Katrina. Yes. We will cover -b over 2a. Yeah, you saw that in the book, I think. Yeah. Yeah, so Katrina saw something reading in the book, this -b over 2a. We will see that formula in a different but related context soon enough. But we'll get there. Okay, so here's the conclusions. Everything that we just built in the chart, we've generalized down here. I guess it's not quite in the same order. If you got 0, that's the one we just talked about. How many solutions were there? Just the one. 1, and it will always be rational. If you got something negative, all right, first of all, for all of the other 2 possibilities, there are 2 solutions, there are 2 solutions, there are 2 solutions. So only in the first case do you get just 1. If the thing is less than 0, we get the i's involved. I said 2 imaginary solutions. I retract that word because we haven't defined it. 2 complex solutions. What page is this on? Thank you. Okay, part C says, all right, now things get a little bit more complicated. Here it's bigger than 0, and here is bigger than 0. So the deciding factor is whether the thing itself is a perfect square or is not a perfect square. Remember the 2 different cases there? So if it is a perfect square, you're going to get a nice number, like that 49 became a 7. Nice means rational. If it's not a perfect square, like the square root of 24, then you'll get messy numbers, irrational. Right? So hopefully we buy into that summary there. It just generalizes what we had in the table. Okay, so why don't we skip that part, jump down to the group activity. Let's make sure that everybody's clear. We'll have 15 minutes, but should be enough time to make some good progress here. You're going to do 3 things for each of these problems. Stick with me for just a moment. You are going to calculate the discriminant. That is a number. It does not have a radical on it. You are going to decide the nature of the solutions. Your choices are the 4 things that we just looked at. 2 irrationals, 2 complex numbers, 1 rational, 2 rationals. Those are the choices. And then finally, you're going to find the solutions by doing the full-on quadratic formula. Okay? 3 things for each. Discriminant, describe the kinds of answers, then actually find the answers. There is an answer key on the next page. We'll work with each other. Raise the flag if I can help.